Welcome, everyone. So this is exam review. So I'm going to show you a flavor of the kind of questions you'll get on the exam. All right, so the exam is 50% of your grade. So it's important. So here are the all the concepts we have covered in the course. C to x86, processes, locality, cache memories, disk storage, linking, virtual memory, I/O, networking, and concurrent programming. So this is the foundation of systems and systems programming that we want you to take from 2310. And this is going to help you in a lot of different ways in the future. You have the foundation and you can take one course on operating systems and networking. And okay, let's talk about the exam. Chapters are posted on the course website. So read each chapter many times. This is my usual advice whenever I teach systems programming, and I use the same textbook. You might not have to do that, but this is ideal. This is if you have all the time in the world, and if you want to prepare fully, read each chapter. We have followed a textbook. It's a very good book and all that. Practice problems, I will be posting a lot more online in coming weeks, coming days, now that I'm done with teaching both my courses. And practice the problems that I show you today. So the topics I want to cover today are C to x86, virtual memory, I/O redirection. So I have problems that I want to work with you on these topics, but you will get a lot more topics in the final exam. These are not the only ones, but this will show you what I want to test out of your learning this semester. Okay. So the day of the exam and all that, all the logistics, we will handle them on the forum, and you must have been communicated about all that. So let's start. All right, so the C code below declares a struct which embeds another struct. The same way we can have two-dimensional arrays. And the procedure on the left operates on this structure. Some expressions are omitted. So someone asked, how much coding will be involved in the final exam? So this is how much coding will be involved. There will be missing pieces. There will be things that you need to guess out of the code. And this is one example. So as a start, what are the offsets of the following fields? P, s.x, s.y, and next. And s is our struct that is embedded inside the struct comp2310. Okay, so the best way to do this kind of question is to just draw a struct. So I have P somewhere, then I have s.x, then I have s.y, and then I have next. So how many bytes are there how many bytes are taken up by P? This is a 64-bit system. So how many total bytes are there in the struct, and how many bytes are taken up by each of the fields in the struct. So how many are taken up by P? Eight bytes. All right. So boot up. The exam is in, if my watch is correct, in less than 20 days. So how many bytes are there in s.x? 2. Short is 2. You need to remember how big is short, how big is int, and you will have all this. It's an open book exam. You'll have all the slides. And how big is next? So a pointer is an address, and on a 64-bit system, an address is 8 bits, okay? So total bytes 20, and the offsets are shown in the figure, okay? So this is a pointer, this is a short, this is a short, and they are laid out sequentially next to each other. You can assume for everything, if two variables are next to each other in the exam, they are sequentially laid out in memory. Okay, so now we have this this piece of code that that is where we have omitted certain assignments. Now, what we want to do is, what we have is the assembly code. So we have the x86 assembly, and we want to guess. We need to fill in the missing expressions in the C code for the function init. Okay, so this looks like challenging, right? So you have the C code on the right. It's missing a few statements, and your goal is, under stress, 3 hours, to do the first question as soon as you can, and look at the assembly and fill in the missing C code, right? x86 to C or C to x86. I'll decide what I want to test. So where should we begin? The argument, when you revise your week 1 slides, week 2 slides, the argument is passed in RDI. So here, if the code is, so we are going to look at assembly line by line and try and guess what is the equivalent high-level statement in C, okay? So what is this doing? It's moving, remember, this is x86, so this is source and this is destination. So if the argument is passed in RDI, argument here is we are passing a pointer to a struct, okay? If the argument is passed in RDI register, then what is this doing, this assembly statement? Not shifting by it, it's adding 8 to whatever is in RDI and moving it to EX. So what is that RDI plus 8? If the pointer, if the argument is passed in register RDI, then what is that RDI plus 8? Oh, we missed the diagram. So what is that RDI plus 8? s.x. So CP s.x. So what this line is doing, it's taking whatever is passed in RDI register, which is CP, the pointer to the struct. This is a load. This is the load from memory. So it's taking s.x. Okay. So this is a get from memory. This is a load from memory. It's loading SCP, dereferencing it, getting s.x and loading it in EAX. What is the next statement doing? moving the contents of EAX to, what is at 10 RDI? So we can fill in our first statement. It's doing this assignment. So this here should be CPS.x. So it's loading CPS.x from memory into EAX and then storing EAX to 10 RDI. And at 10 RDI, we have the second short Y. Okay. So you are going to look at line by line and you are going to fill in the C statements. What is this doing? What does leak do? Load the effective address of, so I could never learn to draw ampersand, so my apologies. What is at RDX? What is in RDI? CP. It's the address of CP dot S dot Y. So it's loading the address of this is the address of operator. So it's loading the address of this field into RAX. And then what is it doing? It's moving it to, what is at RDI? If I give you the address of the struct CP, what does it point to? Without any offset. So RDI points here, sorry, RDI points to this, RDI plus 8 points to this, plus 10 points to this, and plus 12 points to this, okay? So it's storing this thing into P, right? So now we can say this is, so this is how you're going to fill the C statements, okay? Once again, this is loading the address of the field s.y into a register and then storing the register into RDI. And RDI contains our argument. Our argument is a pointer to a struct. And if you just give a point, just have a pointer to a struct, it's actually a pointer to the first field, right? The way the struct is laid out, if I give you a pointer to a struct, it points to the first field. And if you do an offset plus 8, the next field, plus 8, the next field. So let's quickly do the last statement. What is this doing? What is at 12 RDI? Yeah, 12 RDI has next. So it's storing in CP next. What is it storing? What is in RDI? P. Sorry, not P. CP. RDI has the argument CP, right? Argument CP. So it's storing. If we go to assembly, it's taking whatever is passed to this function, which is this, and storing it at an offset of 12. At an offset of 12, we have next. Okay, so you're going to guess what the C statements are by looking at assembly. Now, of course, I won't give you this question on the exam, so it could be reverse. I might give you C, and you might have to fill in the assembly statements. Okay, so the important things we did. So I'm gonna. This is not a regular lecture. I have to move fast. I have to do all the way, all the questions for each topic. Okay. You need to revise loops. You should recognize common assembly instructions, registers. It was a long time ago, and there was no assessment for this. So this might be a little bit. So for while loops Pointer dereferencing, I did almost more than two lectures on that, so you need to revise all that. And array access, remember, we spent a lot of time how arrays look like in assembly. You should be comfortable with, if we give you C code, and we ask you translate into assembly or fill in the missing assembly statement, you need to work backwards, just like we did for the first problem, and understand the width of the array, 4 bytes or 8 bytes. And remember, we were using these offsets and these multipliers with leak instructions. We had these addressing modes where we would do very special things, how data structures are translated in assembly and all that. So I don't want to do this here, but I will be posting problems to help you practice. Loops and array access, you need to practice, and generally C to x86. Caching, I love caches, very important. So dimensions, we have this canonical figure. You need to remember it by heart. The capacity of a cache is number of sets, lines per set, bytes per line. Okay. Associativity, block size. What are these? Given these values, can you tell us where does an address maps to? Is it a hit or a miss? Types of misses. We had the 3C model: capacity misses, code misses, conflict misses. Week 5, part 2, we did an elaborate exercise where we had the simple memory system. That is very important, very important. Understanding of locality. As a programmer, you need to understand the idea of locality. Okay. Let's first do a cache question and then I'll come back to locality. I want to reboot your knowledge about cache and then I'll come back to locality. So the following table, so you might have a question like that. The following table gives the parameters for a number of different caches. M is the number of physical address bits. C is the size of the cache. B is the block size. E is the number of lines per set. For each cache, you need to determine the number of sets, tag bits, index bits, and block offset. So there are 32 bits in the address. The size of the cache is 1 kilobyte or 1024 bytes. The block size is 4. The number of lines. So how many sets do we? Let's do a few of these. So how many sets do we have in this cache? First of all, the way you want to do this is you take the size. So this is your canonical formula, right? So you take the size of the cache. This is your entire cache. First, you determine how many sets are there. Okay. Sorry. First, you determine how many lines are there. Okay. So in a set associative cache, you have many lines per set. Now you can have 1 line per set. That's a direct map cache, or you can only have 1 set. That's a fully associative cache. So the first thing you ought to do is to find out how many lines there are in the cache. So how many lines are there in the first example? Yes. So what's my line size? Which column is my line size or block size? How many bytes are there in a single block or line? That's right here. So divided by 4, what do I get? So I have 256 lines in my cache, okay? So 256 lines, and each set has, how many lines are there in each set? 4. That's E. So divided by 4, I get the number of sets. So 64 sets. High school math, not even high school math, 5th grade. So how many bits I need to index the sets? Two to the 6, 64. Hexadecimal to binary, binary to hexadecimal, 2 to the power 32 to the power 10, 1024. If you spend 10 minutes doing this calculations, then so come prepared. How many bits do I need to index a byte in a block? What's my line size? Where is my line size? 2. So how many tag bits? Whatever remains, 24. So 24 tag bits. Each address in level k plus 1 can map to, sorry, multiple addresses in level k plus 1 can map to a single address in level k. It's a cache. It has limited capacity. So we need tags to identify which address we have cache in our cache. Just like you're building a cache for your proxy, you need some way to remember what do I have in the cache, right? So that's the tag bit that tells you what is in the cache at a specific location. I want to pick number 5. Let's do that. E is 1. What does that mean? 1 line per set. What does that mean? It's a direct map cache. So how many bits do I need? How many bits do I need? So this is my same cache size. How many bits do I need to index a byte in the block? So my block size is 32 bytes, right? So I need 5 bits to, you can fill in the easiest columns first and then move to the next. How many sets do I have? So cache size divided by what? Block size or line size. So what is that? Can someone tell me? So 32 sets. How many bits do I need to index 32 sets? 5. 5 plus 5, 10. What remains? 22. Easy. The dreaded, the fearful virtual memory. Okay, let's do a question on address translation. This problem concerns the way virtual addresses are translated into physical addresses. Imagine a system with the following parameters. Virtual addresses are 20 bits wide. Physical addresses are 18 bits wide. Page size is 1024 bytes. The TLB is 2-way set associative with 16 total entries. TLB is a cache for what? TLB is a cache for page table. Page table resides in main memory. It is maintained by the operating system. Main memory is slow. We want fast access to page table entries. We build a cache. We put it in the actual hardware inside the memory management unit. TLB hit, we win. TLB miss, we need to go to memory and read the page table entry from the page table. The contents of the TLB and the first 32 entries of the page table are shown below. All numbers are in hexadecimal. Okay. Question number 1. The diagram below shows the format of a virtual address. So remember, we have a 20-bit void virtual address. Please indicate the following fields by labeling the diagram. How many bits do I need for the virtual page offset? Virtual page offset is just like the line offset or the block offset in a cache. it's how many bits do you need to access or index any byte inside the page. So how big is the page size? 1 kilobyte. So how many bits do you need for the virtual page offset? 10 bits for the virtual page offset. How many bits do you need for, so how big is the virtual page number? Okay, so we leave the virtual page offset alone when we are indexing the TLB. The TLB is just like a cache because the virtual page offset is the same for all the virtual pages. They do not differ in the first 10 bits. They only differ in the remaining bits. And we use these bits for indexing the TLB. And once we get the page table entry, the physical page, we use the virtual page offset to go inside the page and get the byte that we want. So how many bits do I need to index the TLB? And how many bits do I need for the tag? So my TLB has 16 entries, and it's two-way set associative. How many bits do I need to index a TLB? How many sets do I have in the TLB? Huh? So TLB, so two-way set associative looks like this. You understand how you want me to draw? So 16 entry TLB, two-way set associative. So each set, we do this set associatively for flexibility. So we can put something here or here. If we have direct mapped only one line per set, there are a lot more conflicts. So we have two-way set associative. This is one way, and this is the second way. So 16 entries, two-way set associative. How many sets do I have? 8. Easy, 16 over 2, 8. So each set has 2 lines. So how many bits do I need for indexing the TLB? So these 3 bits are for TLB index, and the remaining bits are for TLB tag. Okay, same idea as in caches, but you're just indexing the TLB by virtual addresses. CPU generates virtual addresses. When you do malloc, you get a pointer back in your user level program. That's a virtual address. The translation happens inside the hardware CPU memory management unit. MMU does the translation for isolation, security, expansion, the virtues of virtual memory, revise those virtues. How many bits I need? So once the translation is done, imagine we have a physical address now. How many bits do I need for the physical page offset? Remember, the virtual page and physical pages in all of our systems are the same size. For convenience, but the size of the virtual page is the same as the size of the physical page. It's convenient. It's very hard to build systems where that's not the case. So the page size means virtual page offset and physical page offset have the same number of bits, right? So 10 bits for the physical page offset, and the remaining bits for the physical page number. So I'm dividing my address space into page-sized chunks, and each of these chunks has a number. The number is here, ppn, and once I get a page number, once I know which chunk I'm looking for, I can use these bits to index inside the chunk to get one of the 1024 bytes. For the given virtual address, indicate the TLB entry accessed and the physical address. Indicate whether the TLB misses and whether a page fault occurs. If there's a page fault, enter blah, blah, blah. So let's translate this virtual address. Okay, so this is where you want to be really, really quick. How much? So 7 is 1. Right? What is 8? Okay. So just a translation from hexadecimal to binary. Okay. The question is, the first thing the CPU does when it gets a virtual address, it does the translate, it accesses the TLB. Okay. So which bits do I need to access the TLB? 10, 11, 12, right? So I need 10, 11, 12 to go inside the TLB, and I need to go with this tag. I may or may not have the translation cached in the TLB. I might have to go to the page table. So what is this? Set number 3. And what is this in hexadecimal? So here's my TLB. Is it correct? Oh. By the way, I was doing it at home and I was also nervous, so I don't know about you. I gave myself 3 hours. I prepared an exam and I was like, wow, this is going to be some exam. Okay, anyway, I'm just scaring you. I'm sorry. So set number 6 and tag is correct, right? So I was kidding, don't worry about it. So I want to go inside the TLB at location at set number 6. Do I have the translation? No. Is it a TLB hit or a TLB miss? So you can feel all this, right? This is 06, 03. TLB hit? No. Once you have a TLB miss, the MMU, the memory management unit, has the right. There's a hardware accelerator built in. It knows how to walk the page table. So it can go to the page table and fetch the entry. So the next thing we want to do is want to go to the page table. The page table is in main memory. TLB is a cache. It's a cache very close to the processor. So for every move instruction or memory instruction, the CPU doesn't need to go to memory because that's 100 cycles. Cache is just 1 cycle. So let's go to the page table. Here's our page table. And what do we need? What are we looking for? We are looking for the physical page number. Virtual page number is generated by the application. Once you are in hardware, you need the physical page number. So it's like a key value store. You give it a key, it will give you a value. But the key is the virtual page number. So what is the virtual page number for this address? The virtual page number is all these bits, right? So what's the virtual page number in hexadecimal? So this is the virtual page offset. And all these bits are the virtual page number. So it's 0, Looks like this, huh? Huh? So what is it? It's 1E, right? It's 1E. So let's go to the page table with 1E. So where is 1E? So we give it a virtual page number, and it gives us a physical page number. Virtual page number, you can have multiple processes. Each process has its own virtual address space. They could both have the same virtual address space, but they are mapped to different physical addresses. Sorry, they could both have the same virtual address. It's just a process with its imaginary virtual address space, but the operating system makes sure that they go to different physical pages. Otherwise, there's interference. Is it a valid entry? So do we have a page fault or no? What is a page fault? Page fault is when the page is not in memory. It's residing on the next level storage, right? Because we don't have enough memory. But it seems like this page is in memory because the valid bit is 1. This is a valid translation. There is no page fault, so no page fault. And what's the physical page number? 57. So now we can re-execute the instruction, and there will be a TLB hit because the memory management unit will fetch this mapping from the page table in memory and bring it close to the processing. That's what a cache does. Now the next question is okay, this is good. So how should so this is my physical page number. Help me fill out this address. So what's the physical address corresponding to this virtual address? So this is the virtual address. What is the physical address? Let's first start with the page offset bits. So where should I get the bits for the physical page offset? They are the same in both cases. You go with the same offset inside the page. That offset does not change. So these bits are the same. 0, 0, 1, 1, 1, 0, 0, 1, 1, 0. And what about the remaining bits? So you have easy, right? You get the physical page number from the page table. The page offset bits do not change because the page size is the same in the virtual address space and the physical address space, and you're done. Okay, let's not do this here. Let's do something else. A question on IO redirection. So remember that. So let's do some storage stuff. So there's a descriptor table for each process, which has a list of file descriptors. So you get the file descriptor, you index this table, and you get a pointer to the file, the actual file that you're looking for. And then there's an open file table that is shared by all processes. So here we have this file descriptor points to file A, this file descriptor points to file B, and the child initially shares the same file descriptors. Okay, so let's look at the question. So the following problems refer to a file called numbers.txt, which has a string 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The calls to read are atomic with respect to each other. The following file, read and print 1.h, is compiled with the following flag. So what does this function do? You give it a file descriptor, and it prints out, it reads one character from the file and prints out that character on the screen. Okay, so this is what the code is doing. Flush flushes the standard output file descriptor buffer. Okay, so you give it a file. So this function is, you give it a file descriptor and it will read one character and output on the screen and add 1 to the file position. So each of these tables has, for each file and each file descriptor, there is a file position field that tracks where we are in that file. If you keep reading a file, it will keep incrementing that position. And dup copies the, if we have dup2 with these arguments, with these two file descriptors. So initially, file descriptor 1 points to A, file descriptor 4 points to B. Dup calling this will copy this file descriptor to the second one, and then both point to the same file. Okay, now both will point to the same file. Here, they're both pointing to different files. So this is what dup2 does. Okay, so what's the output of the following code? So we open a file, file 1. We open a file, file 3. And then we have another file descriptor, which we get from dup2. So it copies file 3. It makes file 3 point to file 2 and gives you a descriptor. Okay, here's the situation. So you have two files. So 1 points to one file, 3 points to this file, and after dup2, 2 also points to this file. Okay? So let's do this. So what will this print? File numbers.txt has, so numbers.txt has 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and this routine prints one character and increments the file position. Okay, so this will print 0, right? What will this print? They are both pointing to numbers.txt, but their positions are different, and the file descriptors are pointing, 2 and 3 are pointing to the same position, and 1 is pointing to a different position. So that's the use of those tables. So the second line will print what? What will the next line print? What about the next one? What about the next one? The last one? So where is the file position for 3 at this point? So this incremented it by 1. So this is where we printed 0. This is where we printed 1. This is where we printed 2. So what will we print now? Okay. So with dup2, we made the two file descriptors 2 and 3 point to the same entry in the second table, which tracks the position. File descriptor 1 has its own entry in the second level table, whatever they call it, for position, and they're all pointing to the same file. But different descriptors are tracking a different position in the file. Okay, so this is, you might want to track, we might give you a, okay, let me show you. We can make it a little bit tricky. Okay, now let's do this. Fork enters the scene. So here we are doing a fork, and the child is executing this code, and the parent is executing this code, and they are both executing this code. So remember, when we do a fork, what is returned to the child? 0. And what is returned to the parent? The PID of the child. Okay. So by doing this in C, there's no distinction between a Boolean and an integer, so we can do this. So who will execute this code? Who will execute this code? Child or parent? If child. So this statement, this if statement is equivalent to if PID 0. Okay. So in C we can say PID. So if PID is returned to the child 0, this will make it 1. So okay. So the situation here is the same as before. So we have 3 file descriptors. We open file 1 and 3. They both point to their separate entries in the table, and they have their position. And there's a file called numbers.txt, and they all point to this. This is the vnode table or whatever. Okay. And then file 2, once again, we copy file 3 into file 2, the descriptor entry. So 2 also points to where 3 points. Now let's do it. So what will these 2 lines print? Our string is 0. It says file 1, file 2. File 1 and file 2, are they pointing to the same entry in the table or different entries? Different entries, right? So they each have their own position. So the first one is incrementing file 1. The second one is incrementing file 2. File 1 points here, file 2 points here. So 0, 0, right? So now what happens? So in the parent, so the parent goes here, and wait means it needs to wait until the child is done. If I don't put a wait here, you can spend 1 hour on this question, but I want to put waits properly to help you, because then it's a matter of who goes there first. Then it's not a matter of one output, it's a matter of that question would be which of the following outputs are valid. But okay, I'll see how my mood is on that day. So this means that the parent is now sleeping. Okay, so child will execute this, right? Child, whenever you do fork, child inherits the file descriptor tables of the parent. Okay, so what will this print? Good, 1, because file 3 and file 2 point to the same entry in the position table. File 2, we have already printed, we have already incremented. This here is now +1 after this. Okay, now child closes the file descriptor and opens a new file descriptor. So now child will have a new file descriptor that the parent does not have. Okay. And it will have, let's say, child will now have a new descriptor which will point to a new entry in this table, and initially the position will be 0. So what will this print? What will happen next? The parent is waiting. Are we done with the child? No. Both parent and child will execute this. So what will be printed by the child here? Child was here. It opened a new file descriptor. It printed 0 and position +1. So when we go here, we print 1. Okay, now things are interesting. So now the parent wakes up. The parent wakes up, and now the parent needs to do. The parent needs to do these 3. Now, what will the first line is tricky. What will the parent print here? Where is file 3? Where is the parent's where is the parents, what is the parents' position of this at this point? Child inherits the exact copy of the parents' file descriptor tables, and it gets a new entry in those tables if it does an open. If it doesn't do an open, it has the exact same copy of whatever parent and the child share these tables. Okay? So with this information, and new entries are created in these tables for the child whenever the child does an open. So with this information, where is the parent's file tree or file 2 position? This was 0 by the parent. Sorry, this is an open. This is 0. Was there any other read from this descriptor? No, there was. This read over here, this one. Child inherited the same table, the same file descriptor table as the parent, and it did a read. So this one, the parent will now see 2, 3, 1, and what about this one? Where is parent right now with file 2 and file 3? Okay. So this is a subtle thing here, that the child and the parent, they share the file descriptor tables, and new entries are created in those tables for the child when it closes or opens a file. Otherwise, they share the file descriptors, right? And they will see each other's offsets. So the best way to do a question like this is to start with this figure on the left and track the positions. Honestly, you can do it in your head with some practice. You don't need an Excel sheet. It won't be that big. And really understand what DUP2 is doing. Concurrency, races, and synchronization. Consider a simple concurrent program with the following specification. The main thread creates 2 peer threads, passing each peer thread a unique thread ID, and then waiting for each thread to terminate. Each peer thread prints its thread ID and then terminates. Each of the following programs attempts to implement this specification. There are some incorrect, some of them incorrect because there's a race on my ID. That makes it possible for one or more peer threads to print an incorrect thread ID. Except for the race, the programs are otherwise correct. You are to indicate whether or not each of the following programs contains such a race on the value of my ID. So it says here you will be graded on each subproblem as follows. So I might do that because I want to prevent you from taking guesses, wild guesses. I might say that if you're wrong, you get -2. If you're correct, you get +5. If you don't answer, you get 0. Okay. But if you just take a wild guess, let me try my luck today. You might get a negative. So I forgot to put this here. Is there a race on my ID? Okay, main thread, what is it doing? It's creating 2 threads and it's passing as argument a pointer that it allocates an integer on the heap, and it passes the address. It dereferences that to store the integer ID of each thread, and it passes a pointer on the heap to the thread, and the thread dereferences the pointer and does something with it. Is there a race on my ID? No, because each thread has a separate copy of my ID on the heap. So this will create, if this is our heap, This will create two integers on the heap, and it will give each thread, let's say 0 and 1. And the threads here will do the dereferencing and free and print. So there is no race on my ID, right? Is there a race on my ID in this code? So what are we doing now? We are passing the address of stack variable I. Is there a race on my ID? There is a race on my ID. While one thread is dereferencing the stack variable might get updated by the main thread. There's a race on my ID. Is there a race on my ID in this code? We are passing the value of the stack variable as argument. Is there a race or no? This is copy by value. So each child will get, oh, sorry, not child. Each thread will get a copy of integer I, and that will be copied onto its stack before the function call is made. There is no race. Is there a race on my ID? We are passing the pointer to the stack variable, and then we have P and V operations to protect the this is tricky. Is there a race or no? I believe there is a race. Before a thread does the P operation, the main thread might execute the second iteration of the loop, right? It seems there is a race. Okay, so you will have questions like this. So we'll give you code. You're gonna have to write code, and please don't start writing the programs in VS Code and executing them. that won't. You're gonna waste a lot of time. You need to reason about these things. And okay, let's do something else. So you can look at those questions. Consider the following. If you like race. Identifying races, there are more. I'm just skipping to give you a flavor of more questions. Consider the following C program. And the question is, for each of the following strings, circle yes or no if this is a possible output of the program or no. So this is where I'm saying, if you circle no, you get 0. If you take a wild guess and you're well, if you're right, you get 2 and you get -1. Okay, anyway, we might not do that here. I don't know what the ANU policy is. Okay, so let's try to understand the program. Okay, this is interesting. You will have questions like that. Okay, what you're going to guess is this output possible or no? Okay, so you have a bunch of choices. So how do you attack a question like that? So here we have, wherever you see F flush, it's trying to flush the standard output buffer because the standard C library has its own heuristic when to flush the buffer. So here we are forcing right on the screen. So value is 2, and then we are saying printf 0. So the first thing that is printed is 0. So if you ever see an output that starts with 1 or 2 or 3, you know that that is not possible. Okay. So here we don't have that. So the first thing is 0. Who will execute this, parent or child? Who gets 0 from fork? So this is child and this is parent. So notice that by putting the weight here, we have opened up the option of multiple outputs, multiple possibilities, because now child could execute first or parent could execute first, and we have to figure out which output is not possible. So there are two possibilities. If the parent executes first, what will be printed here? So this is val minus minus. Val is 2. So if the parent goes first, what will be printed? If the child goes first, what will be printed? Okay, so we now know that nothing else is possible. So 0, 4 is not possible, right? So let's cancel all. If there is any 0, 4, let's knock it off. But there is no 0, 4. They're not making your life. We're not going to make your life that easy. At this point, let's just do one by one. So let's take the first one, 0, 1, 4, 3, 2. So how do you tell if 0, 1, 4, 3, 2 is a valid output? So clearly, it's a case of parent executing first. So let's keep executing the parent. So if the parent executes, and then it's going to wait. So it's not going to execute all this, right? It's going to wait for the child. So let's go to the child. What is the child going to print? Child is going to print. So parent did its part, 1, and it's waiting. What is the child going to print? Three or 4? Val is 2 here, and when the child does val plus plus, it's 3. It seems that 0, 1, 4, 3, 2 is not possible, right? So let's pick the next one, 0, 1, 3, 4, 2. So since 0, 1, 4, 3, 2 is not possible, so what is possible? So child prints 3. Parent will not wake up, right? Child needs to finish all this. So this is doing val plus plus and printing something. So this will be 4. And then the parent will wake up and print what? 2. So 0, 1, 3, 4, 2 is possible. Let's take 0, 3, 1, 4, 2. Can you tell from the previous exercise, like when we did B, is 0, 3, 1, 4, 2 possible? So we start with 0. 3 is when who goes first? The child goes first. So 0, 3. The child goes first, prints 3. Parent prints. It's possible, right? Parent could first the child executes, does a little bit of work, then the parent does a little bit of work. Now parent must wait, but the child will go and print 4, and then the parent will wake up and print 2. So these are not hard if you have a good strategy. So this is also possible. Now 0, 1, 2, 3, 4. Is that possible? So this is 0. Parent goes first, prints 1. Then not possible, right? Not possible. How can you print 2? Because after this, after 0 and 1, the parent has to wait, right? So child will go ahead and print 3. So this is not possible. 0, 3, 4, 1, 2. So 0, this, 3, child. Child goes ahead and finishes. Parent does something, and then because the child is done, it goes here, and so that's possible. Okay, so that's not hard. So you wanna start this type of question by eliminating. This is SATs. By eliminating all the choices that are not possible. Okay, and then moving on one after the other. The following instruction sequences belong to the execution of 3 concurrent threads. the 3 threads execute on a 4-way hyper-threaded processor. Okay, so now this is an out-of-order processor. This is a hyper-threaded processor. We can execute instructions out of order as long as we don't violate a read after write dependency. Like we cannot just go ahead and start executing if we don't have the value. The scheduler is trying to fill 4 issue slots with 4 instructions with the goal of generating as many memory operations as possible. Which of the following combinations are valid? Okay, so the first thing you want to do when you get a question like that is not panic. The assembly here, we're now testing your assembly skills. Okay, if you think about it, this is a swap operation. You are bringing something from memory, storing it in a register, bringing something from memory, storing it in a register, and then moving the registers to different locations. So you're swapping 2 variables. These 2 instructions and these 2 instructions are exactly the same, except here we're using REX, here we're using RBX. What is it? It's a joke. Here we are adding something to RCX, then we are adding RCX to RDX, then we are using RDX, we are loading something that is at address RDX into RBX, and then we are moving RBX to blah. Okay. The processor's job is the scheduler. We want to build a scheduler. So remember, in a hyper-threaded processor, you can take instructions from different threads to fill all the issue slots. So all your functional units are busy. Here, the scheduler is trying to generate as many memory requests as possible because that's important. Each memory access takes 100 cycles. So we want to keep the memory busy. We want to send as many requests as possible to the memory system in each cycle. So this is the first cycle. And the scheduler is trying to get as much work done as possible, where the definition of as much is the maximum number of memory operations. Okay, can we issue? And the color code means that these 2 instructions are instructions 1 and 2 from this thread. This is instruction number 3 from this thread, and this is instruction number 4 from this thread. Is this a valid combination? Where valid means we are not violating a read after write dependency. If instruction 1 produces a register R2 and instruction I2 consumes R2, then we cannot execute I2 before I1. That's the definition of validity, read after write dependency. So for instance, you can't just execute this instruction because first you need to compute RDX, right? An out-of-order processor can execute instructions out of order as long as there are no dependencies. If there are dependencies, then you need to execute this first, then this, okay? Can I execute these 2 instructions in one cycle? Can I issue these 2 instructions in one cycle? Is there any dependency? So in A, this is correct. So an out-of-order in a hyper-threaded processor can take 2 instructions from thread 1. Now, and that's the beauty of hyper-threading. Now you have 4 functional units, you have 4 issue slots, but thread 1 does not have any. I cannot execute instruction 3 and 4 because I need the results from memory before I can execute instructions 3 and 4, right? So instead of wasting an issue slot, we go to the blue thread and we take this instruction. And we take this instruction. Is this a valid combination of instructions or no? No. The processor has violated, in an attempt to be aggressive, the processor has done really something really wrong. It has violated the read after write dependency. Read after write. Read this after it's been written by this instruction. A previous instruction is writing it, and third instruction is using it. Processor cannot go ahead and violate this dependency. What about B? So this is correct, this is correct. This comes from here, and this comes from here, this instruction needs RDX, and for RDX, this instruction, okay? So you cannot execute this load, before you execute these instructions. So this is also wrong. What about this one? 1, 2, again, correct. Can I execute the first instruction from the green thread, right? What about the third instruction from green thread? Is it a dependency? No. RDI is not written between these two instructions. So this is a valid combination for the hyper-threaded processor. What about the last one? Correct or no? Correct. Okay, so not hard. Looks as if there's assembly, there's boxes, colors, and all that, but it's easy. As long as you know which slide to go in the lecture content to learn about hyper-threading during the exam, right? Sequential consistency. Consider the execution of following concurrent processes on two different processors. A and B are originally cached by both processors with initial values of 0. Under sequential consistency, which of the following outcomes are possible? Sequential consistency means, in a nutshell, you respect the ordering of instructions within each process. Across the two processes, the interleaving is arbitrary. You must not violate the ordering of instructions within A equals 1 must happen before A equals 0. This if statement must happen before A equals 1, but across the two threads, you can have an arbitrary interleaving. What about this one? Is it valid or not valid? So imagine that P2 is stalled. P2 does nothing. P1 executes first, and initially A and B are cached with initial values of 0. If processor 2 does not do anything, what will happen to the branch instruction? Taken or not taken? So this is tricky. So it will be, so let's say not taken. So if this is not taken, it means what? That B is 1. And if this is not taken, it means A equals 1. So it's possible that we have a sequence of instructions where this happens, then this happens, then this happens, then this happens, then this happens, and then. So this is a valid interleaving under sequential consistency. And this will lead to not taken, right? B is 1, A is 1. So these two, this will be not taken, this will be not taken. Because this is taken if B is 0. So it's not taken because B is 1. So this is valid. What about this one? Under sequential consistency, is it possible? Okay, the way to reason about it is as following. Let's say the red one is taken. If the red one is taken, then this must have executed, right? And so this is taken. Now, if this branch has executed, what does it mean under sequential consistency about this instruction? What does it tell us about this instruction? It must have executed. Under sequential consistency, if the branch is executed, then the assignment above it must have executed. We must not violate the ordering of instructions within each process. If this is executed, then it means that this cannot be taken. Under sequential consistency, taken is not a valid outcome. This is the kind of model we give to the programmer. Programmer, if you're not going to use locks, if you're going to write nasty programs, then this is, you can reason about the correctness or what will happen using this model. Okay, but we don't do this. We have better ways of dealing with. But this is the model. This is what will happen if you're running two processes on two different processors. We are giving a specification. What are the possible outcomes? Okay, so this is not possible. Does everyone understand this? Right? Is this possible? So what kind of interleaving will give you this? So this is taken. So it means that B equals 0, B equals 1, then so if red is taken, okay, sorry. If red is taken, then A equals 0. So at this point, red is taken. So how will B not be taken? Right, it's correct, right? So then B equals 0, B equals 1, if A equals 0, right? Right. So the last if statement will not be taken because A is 1. And because this branch executes before the B equals 1 assignment, this is, so 3 outcomes are possible under sequential consistency. And the programmer can be 100% sure that taken can never happen. And this helps you write parallel programs and reason about it. Okay, deadlock. Two threads, X and Y, access shared variables A and B, protected by mutex A and mutex B. So these are the two threads. I'll let you go after this one. So this is the last one. So shared variable A and B. So this is, so obviously it's an exam question. So clearly a programmer will never do this. There is something wrong with this. And we have to figure out what is wrong. Okay, they're protected by mutexes. All variables are declared and initialized correctly. Show an execution of the threads that results in a deadlock. So deadlock is when both threads are trying to do something. Oops, sorry. Each thread wants the other thread to do something in order to make progress, right? So thread A wants something from thread B, and thread B wants something from thread A, and so they are both stuck because there's a deadlock. So how can this happen here? So programmer has done something really, really smart. It's done a P operation on A, then done a P operation on mutex B, and then V on B and V on A, reverse order. And this thread is doing a P operation on B, P operation on A, and then the V operation. So let's do this together. So how can we have a deadlock? So in real world, when you run this on a multi-core processor, all bets are off. What happens first, we don't know. Depends on many things. Caches, this, that. So let me start this by saying, let's say this happens first. Thread A gets a lock on mutex A, then does this. So what can happen now for a deadlock? What would lead to a deadlock? If the second thread does okay, this is a situation. Can any thread make progress now? Thread X wants a mutex P, so it will sleep because mutex B is greater than 1. Thread Y will sleep because it wants mutex A. And so we have a deadlock. Both threads are now waiting for each other to do a V operation, but so we have a deadlock. So how should we solve this? Okay, there are different approaches to solve the deadlock problem. Modify the code above to show 2 approaches to prevent deadlocks. You can declare new mutex variables if required. Do not change the order or amount of the increments to A and B. Rather, change the locking behavior around them. The final values of A and B must still be guaranteed to be incremented by 60. Okay, I leave it to you. Are there any quick ideas? What? We can introduce a new mutex that prevents B from acquiring. So, okay, that's a good question. So I need to be careful how much constraints I put on this kind of questions. You can declare new mutex variable if required. Do not change the order or amount of increment. Okay, let me tell you that sticking a huge giant lock on the entire program, don't do that. we are trying to make you clever, preparing you for real life. We are not preparing you for okay, I don't want to make fun of Optus again, but I've done that a lot in the last four weeks. Right. So if you just, so help me here. So what should I do? Grab a mutex BA. Is this something really quick I can do? I cannot change the ordering of A and B because that will be a different program. It seems that you need a new mutex variable. If X has A, okay, let's think about it offline. There's a couple of ways you can do it.
After the first B property and pull B on the next A, and then like another B afterwards, and you check it again.
So in thread X, what should I do? So this
after the A property 10, pull B on using A.
Okay.
And like same thing with thread Y, B on B after B property 10. Basically just like log and unlog immediately after you've done the check.
Yeah, okay, good. Yeah, that's a possibility. Looks like a possibility. Yeah. Is that enough for what the exam would look like? Now we are really done with this course. Okay, I was planning to do another one, but I don't think it's necessary. This we can do a meetup in the middle of the November 10 if it's necessary. I don't think it's necessary. Just prepare in your. You have to go through the material yourself. And you have to practice the problems. There's still problems on the website. I'll post more. You have to go through these. But this is what we want to test. We don't want to make you write code. We don't want to trick questions, stuff like that. Okay. All right, take care.
I had a question on the hyper-threading side.
Yeah.